please hit subscribe.
So in this video, we will show that these two limits or sequences are convergent and that their limits are the same. So our strategy will be the following. First, we're going to show that a sub n is greater than b sub n for any value of n. For some of you, this might be obvious because what we see here is that a sub n is the arithmetic mean of two numbers and b sub n is the geometric mean of the same numbers. And we know already that arithmetic means are always greater than geometric means. But we're still going to show this in the next slide. Why do we need to show it? That's because we're going to use it to show that a sub n is decreasing and bounded. And if it's decreasing and bounded, monotonic decreasing and bounded, then we have a convergent sequence. And we know this from the fundamental axiom. So we decided that our fundamental axiom will be the assertion that the number line does not have holes. And I'm just going to put a link here to our video on that. Then after we've done that for a sub n, we're going to do the same for b sub n. We're going to show that b sub n is also convergent and it is increasing and bounded. And lastly, we're going to compute the limits of both sequences and show that they are equal. So first, the arithmetic mean is always greater than the geometric mean. So this is what we want to show, or if we write it slightly differently, we want to show that a sub n minus b sub n is greater than 0. So let's just write down a sub n. So it's just the arithmetic mean of a sub n minus 1 and b sub n minus 1. And b sub n is the geometric mean. Then we factor out 1/2. And then we observe that this is a perfect square. And because this is a perfect square, this is always positive. And therefore, we have shown that this expression is always greater than 0. And therefore, a sub n is greater than b sub n for all n. Now, let's show that a sub n is convergent. First, let's show that it is decreasing. So, why do we think it's decreasing? It's decreasing because a sub n is the average of two numbers. And the two numbers are b sub n minus 1 and a sub n minus 1. And their average must be in between, right? And what is their average? The average is a sub n. And then, we also know that b sub n minus 1 is always less than a sub n minus 1. And this is what we showed in the previous video, or rather in the previous slide. And so, the inequality symbol looks like this. And what do we see here? We see here that a sub n is less than the preceding term. And this is what a decreasing sequence is. The terms in the sequence are always less than or equal to the preceding term. And so we've shown that it is decreasing. Now let's show that it's bounded. So we know that a sub n is less than a sub n minus 1. But we also know that this applies for any value of n, and therefore a sub n minus 1 is also less than a sub n minus 2, and so on until a sub 1. But what does this mean? This means that a sub 1 is in fact the maximum value, or the upper bound for your a. And here we know that this is positive. All a's are positive, so we have 0, and so it's also bounded below. So what we get is 0 is less than or equal to a sub n, which is less than or equal to, but actually strictly speaking less than, let's just put equal to a sub 1 for all n. And therefore, it's bounded below and bounded above. So we've shown it's bounded, and therefore, it's convergent. Now let's show that b sub n is also convergent. And here we will show that it is both monotonic increasing and is bounded. So how do we show that it is monotonic increasing? Well, b sub n equals the geometric mean of a sub n minus 1 and b sub n minus 1. But we know that a sub n minus 1 is always greater than b sub n minus 1, right? This is from this fact that the arithmetic mean is greater than the geometric mean. And we've shown this in the previous slide. So now that we know that a sub n minus 1 is greater than b sub n minus 1, and this part here remains the same, now we have this expression, and this expression here is also equal to b sub n minus 1. And therefore, b sub n is always greater than b sub n minus 1 for all n. And this is exactly what we mean by an increasing sequence, right? That the term is always greater than the preceding term. Now, let's show that it is bounded. So, we know that a sub n is always greater than b sub n. But we know that a sub n is bounded above. We've shown this in the previous slide. And the maximum is a sub 1. And we also know that these terms are all positive, right? And therefore, b sub n is bounded above by a sub 1 and bounded below by 0. And therefore, b sub n is bounded. And thus, it's convergent. Now, we've shown that a sub n and b sub n are both convergent. Now, let's try to get their limit. So, suppose that alpha is the limit as n approaches infinity of a sub n. If that's the case, then if we take both sides of this equation here, we get this. And also, let's make the definition of beta to be the limit as n approaches infinity of b sub n. Now that we have this limit, here what we have here is just alpha, right? And here what we have is 1/2 alpha plus beta. And then what we can do is the following. Therefore, alpha equals beta. So, we have shown that both limits must be equal. Please hit subscribe.